Hello community! We have some new research insight by Harvard University, MIT and Cornell University on artificial intelligence. And artificial intelligence is of real importance because according here to the latest article in Business Insider, Goldman estimates that in the next few years the tech companies will invest more than $1 trillion to develop AI, and Microsoft is one of the biggest spenders. Microsoft's capital expenditure hit a record $20 billion in its most recent quarters. So the implications for everything that is done or connected with AI is significant. Let's have a look at a new research study. Now the title is a little bit vague, evaluating the world model implicit in generative models. Let me translate this to you to do LLMs really understand the task given? And you might say, yes, of course, because LLM achieve a very impressive high next token prediction accuracy in all the tests, no? LLMs are amazing. Yeah, you're right. But the question here is a little bit different. They say here, hey, does our LLM models implicitly learn world models? Now, let's think about this. We are talking here about, in AI, about the emergence of intelligence. And now the question is, at first, does this emergence of intelligence exist? And I just went to ChatGPT for Omni and I asked, hey, what is this emergence of intelligence in these AI systems? And ChatGPT comes back and says, yeah, it refers an observation that certain complex behavior, problem-solving abilities, and conceptual understandings spontaneously arise in our models when humans give them certain tasks and humans see the result. And I say, hey, is it real? And ChatGPT for Omni comes back and says, So we have evidence, have documented this. And looking here at the benchmark, it is clear that the models, the LLMs, perform above the human expectation, therefore suggesting here those capabilities, rather than a simple memorization effect of the AI itself. But it also gives us here the information about a controversy. And it says critics argue that calling this phenomena intelligence might anthropomorphize those models as they lack consciousness or intent. So whenever you hear me saying here on my YouTube channel, hey, I like this LLM, or I like Gemini models, or, I almost do anthropomorph these models, I treat them like a human being and I have my conversation as they would be another human being. And for Omni comes back and it says here, the illusion of intelligence is possible, so some emergent behavior could be artifacts of clever interpolation in the training data, or emergent capabilities might depend heavily on specific data sets or the training regimes that are not publicly available for some models, raising therefore questions about their generality. So maybe this was in their training data, but since the training data are not published, we can't know this. So therefore, the AI itself tells us, hey, our models, our LLM models perform above human expectation, suggesting that those capabilities are there rather than a memorization effect, but because specific training data regimes are not public, suggesting. Great. So what about if we have another idea? I mean, not we, the researcher publishing this. And they say, hey, does our LLM really have an inherent representation in its tensor weight structure in the transformer architecture? Has it learned world models? And you might ask, what are world models? And it is simply a model of the human world. So this means it is an internal representation by the LLM of the combined objects that the human language describes, because we have a large language model. So, simple idea, let us verify this statement. So, what we just need to do is to rebuild the human language on mathematical logical principles to perform operations in order to validate here a human statement, like this one here, given in a human language. And a visualization, for example. What is a world model here in the easiest form that you have an idea? We map each street and each intersection of the highways and then use here a simple search algorithm to provide direction if you're driving with your car. So the world model is here our street map in the easiest idea. Now, language models are different. Language models now collect simply in their training data set turn-by-turn sequences of taxis of cars from trips in a city and then train a sequence model on them. So to show you this here, we have a start point and a finish point, and then we have a left turn. We continue with the next at the next intersection, and we go to the right. We continue, we go to the left. We train a sequence model on this data, and then this is the world model of our AI system, of our large language model or vision language model or whatever. So you see, the language model are completely different. So if the sequence model now successfully recovers the world model, we would obtain simply a map of a specific city without ever mapping this. And we have a simple routing algorithm to predict the next turn. And if you think this is simplified, no, this is exactly how the LLMs are currently used in scientific domains, in protein generation, in genetic research, in chemistry, but also in the application medicine, finance, and other domains. So this has some direct impact on the performance in real-world examples. So let's validate this idea. Hopefully, we will use here now Noam Chomsky, because in the 1950s, he devised here an abstract representation of the formal and the natural languages known as the Chomsky hierarchy. And the hierarchy in the fields of formal language theory, computer science, and linguistics here is a containment hierarchy of classes of formal grammars. We know this. A formal grammar describes how to form strings from a language vocabulary or an alphabet that is valid according to the language syntax. So we use here the linguistic research since we are talking here about a large language model. And we will use here in Chomsky's hierarchy a type 3 grammar, because this will generate here the regular languages. And you know from informatics, computer science, that the automata theory is closely related to the formal language theory, for example, by Chomsky. So what we will use now, given that we talk about language model, we will use here the insight for the formal language theory, and then understand, as it's already proven, that there's a direct link to automata theory, and then we will use here informatics, the insights that we already have for decades of research in automata theory. Now, automata are used as a finite representation of formal languages that may be infinite. Automata in computer science are often classified by the class of formal languages they can recognize as in the Chomsky hierarchy. So this is the interrelation we're going to build upon. And here you have it. At the core, you have a simple combinational logic. Then, a higher complexity, we have a finite state machine, a push-down automaton. And then finally, the most advanced one is the Turing machine. So an automaton with a finite number of states is called a finite automaton or a finite state machine. And this is the instrument we're going to use. So we're not going to use it just the logical, the easiest one, the combinational logic, but we're going to use here the next most simple finite state machine. Let me give you an example, because always an example helps. No? Imagine a vending machine. A vending machine has very few states that the machine is in. No? Ready? It's just waiting for your money that you put in the coins. Then this next state is, I have now received enough money for the next operation. So you put in enough money to buy something from this vending machine. And the third state is here, dispensing. The machine gives you now the snack that you selected. So this is a DFA, because you can perform actions like input, like inserting a coin or pressing a button on this vending machine. And depending on the current state and the input function, the machine transitions now to a new state. So for instance, if you're in the ready and you insert a coin, you might move to the enough money. If you press a button in ready, nothing happens. You stay in ready because our criteria, enough money, is not met yet. But if you press a button in enough money state of the machine goes to dispensing you and gets you the snack. So you see, this is the easiest construct we can build, and this is a very simple example of this. So this vending machine example shows you here a simple DFA fixed set of states, we have some specified input, and rules for transitioning between the state based on the input only. And it is deterministic because given a state and an input, there is only one possible next state. And it is finite because it only has a limited number of states. So this means that the world, and this is a term that we have to define in mathematics, no? In a scientific domain or in the world of logic or causal reasoning, can be now modeled as a deterministic finite automaton from informatics or computer science. So as the automaton sees now a symbol of input, it makes a transition, it jumps to another state according to its defined transition function, which takes the previous state and the current input symbol as its argument. Transition function with some arguments, and we have here the transition happening. And if you want a pure mathematical definition, a DFA is a 5-tuple. So we start with a finite set of states. We have a finite set of input symbols, a transition function that maps a state and an input symbol to the next state. We have the initial state and a set of accepting states. Now, since those are now theoretical machines we use in computer science now to model the computation itself, guess what? This is now the instrument, the tool we're going to use now for our exploration here. Do LLMs really understand the task? So we have now, Harvard, MIT, and Cornell researcher had this new idea. Hey, we build a new framework. A new framework to interface between the generative sequence model and the world models represented now by our deterministic finite automata, by our machines. And both of these, our LLMs and our automata, are built on a shared scaffolding of tokens, sequences, and languages. Of course, both have to have the same language basis. Great. And then we just have one condition. The ground truth sequences used to train and to test here our LLM belong to the language of the deterministic finite state automaton. Of course, otherwise it would make no sense. No? Great. So we have now that we are able to build our world with our DFAs, and then we have our LLM, and LLM have a perfect next token prediction mechanism, beautiful self-attention layer, everything is there. So now let us examine if our large language model have a correct internal representation of the world, of our human world. Let's say we apply it for reasoning, for building new molecules in chemistry or biochemistry, for financial transaction, for evaluating the risk in transaction, for a simple gameplay, or if you have some logic or whatever are your applications. Now you might ask, hey, why you go here not with a lower level Chomsky grammar? Why not turn here to level 0 and the Turing machine? Huh? Well, we want a simple example, and DFA represent here a really well understood class of computational models with clear notion of state and transition, and I think it is just simple. We want to be simple to reduce here the mistakes that we can make. And Turing machine are not at all simple. So, by assuming that the underlying world of a transformer is trying to model is now represented as a DFA, we can leverage the theoretical tools of automata theory to analyze the transformer internal representation. Please focus on this. We can use everything that we know from automata theory, from informatics, from computer science to analyze now the transformer representation that the transformer has in its dense network here of tensors. And then there is something beautiful. Then we can measure if the LLM has truly learned to understand the states, the transition, and the logic governing here the sequence generation, or if our LLM is just superficially mimicking the observed sequences of its pre-training data sequences. Left, right, continue. So we have built now a new framework with some beautiful ideas. We combine here whatever we know about language, semantic languages, regular languages, and so on, now with our insight from informatics and computer science. Now, in order to apply these tools that I mentioned here, now you have to know a little bit about informatics, computer science, but if you study this, no problem, go back to your textbook. You have there the Myhill-Nerode theorem, and this provides you a precise way to characterize the state of a DFA in terms of the sequences that they will accept. For a very short, unscientific explanation here, informally, we can say that two states are distinct if and only if there exists some future sequence that is accepted from one state but not by the other state. Really easy to imagine. So, in our vending machine example, ready, the state of ready and the state of I have enough money are distinct because pressing a button leads to a snack in the state of enough money. But if I press a button in ready and have not inserted the coins, I will not get my snack. So you see, distinct. Simple, isn't it? So, now the researcher in this new preprint use here the inside of the Myhill-Nerode theorem as a foundation for two new evaluation metrics. And you might say, why do we need this? Well, we know LLMs are great in predicting the next token. But predicting here a sequence does not mean understanding what is behind the sequence. Understanding here the structure of the logic, why those sequences are generated. So therefore, with a little bit of mathematics you find in the paper, they come now up with two new evaluation metric systems. And the first here is a sequence distinction metric, and the second is a sequence compression metric. If you want to just have a look, I give you just an example, maybe it is easier. So for a sequence distinction, imagine our LLM understanding that being at two different intersections at a highway, no? Two different intersections or in a city, allows here for a different set of next turns. Because at one intersection you might have a right turn allowed, and the other intersection you are not allowed to turn to the right with your car. Sequence compression, a lot of mathematics, but it is a simple example. Think of it like testing whether the model understands, the LLM really understands, that different driving routes ending now in front of the same intersection should have the same set of possible next future turns. Because you are standing really at the identical intersection. You just have a different path how you arrive there. Therefore, the system should, the AI, our LLM, should be able to understand, hey, those both cars coming from different routes, they have now the same set of possible next turns. Turn to the right, turn to the left, cross, whatever. So, very simple evaluation matrix systems, but very powerful because now the impossible is going to happen. And now the researcher in this research preprint uses here DFA to represent the true world model. And they have New York taxis here, and the DFA now represents simple the street map. So the states are the intersection and the destination pairs, and the transition between the states are valid movements between those intersections. Great. Now a transformer model is trained to predict the next direction in a sequence, given the origin, the destination, and previous direction. And if we use now this transformer that is now trained on the same data, and we look at the internal representation of the transformer, what the transformer understands from all these commands of thousands and thousands of taxi rides. This is now what a transformer has as an internal representation of the world, of reality, of the street map of Manhattan. Now, 2 points maybe. If you enter your cab, your taxi here, and you go here where you see there's a lot of training data, the taxi has done this way a long time, and you go here, start, end of your taxi ride. If you are here where you have a lot of training data, you have no problem, oh, it's perfect, it is great, yeah? There are all the training data, this is known. But if you would like to go here where there are no training data, or maybe here where there are not enough training data, or here where there is kind of a void of known examples of rides taken there, There's a reason, but you have not emergence happening that the system understands how to go there, how to pass there, and have this sudden uprise of intelligence. You see here a representation of the pre-training data set, the LLM, encountered here in the sequence-to-sequence model. So what does it mean? It means that our LLMs, our generative models, our vision language model, whatever, they can be deceptively good at mimicking a behavior without truly understanding the underlying logic, the underlying structure, or the underlying complexity. So our LLMs are perfect mimicking behavior systems. Now with this new evaluation matrix, think about, up until now we only had this predict the next token metric evaluation. No? Think about, for a car it is, can you go in a straight line or can you accelerate in a straight line? And now you want to investigate the model, hey, can your car go in a curve, have a right turn, have a left turn? Now you need a new evaluation metric. Evaluate if the car can deviate from a straight line and take a left turn. So, very easy explanation for evaluation metrics. Should assess not just what the model does, predict the next token, but what it knows. So, this Myhill-Nerode theorem offers now a powerful, quotation mark, new framework for probing this knowledge of our LLM with a new evaluation metric. So the key finding is more or less that those LLMs that we use daily, I use daily now for more than 3 years, they can achieve a high next token prediction accuracy. Great, fantastic. But without genuinely understanding the underlying structure, the underlying world model, the underlying logic. And you see this because these neural taxi models here could plan routes really effectively, given they follow here the known patterns, the known training data. Yet their implied street maps were incoherent, and especially if we were told to a taxi, hey, detour, don't go your standard route, you follow your standard pattern, but take here this street to the left or go another path, then the systems almost break down. And you say, but wait, I have a solution to this, no? We just use a graph. Surprise, surprise, this is exactly what the researcher did, no? Taxi ride obeys here true world model. The weighted graph corresponds to the system of intersection street. So they define the graph where V is the set of intersection, E is the set of street, and then we have a weighting function containing the distance of each street, and then an age label, and you get it, and we have finally 4,580 nodes. This means the intersections, and we have 9,846 edges in the streets, and it stays the same, the result. And yes, I know what you're thinking. Me too. I have minimum 7 additional ideas. I could use another intelligent tool now for LLM. No? I have other methods here of augmentation verification. But you know, all of this is just to force now the LLM to behave in a certain predefined way that I want the LLM to behave in a certain predefined pattern. But this is not the topic of the study. I know AI can follow patterns. What I was interested in, are AI systems intelligent? And the result is the AI model, my LLMs, they do not understand the reasoning. They do not understand the real-world structure. They do not understand the real-time complexity. This means the correct internal representation of the world. They don't have it yet. So, talking about emergence in AI, I just have a big question mark. And you know, we started with general intelligence, and then we went to super intelligence, and then just recently I read a paper here, and this is a YouTube video with hundreds and thousands of likes and views, hyper intelligence of AI. But you know now, watching this video, well, maybe the reality is different from the hype. But let's come to another problem. And this is really, I want to include this here in my video because we face now a problem. And I started here with this publication that I read, and it's not sponsored by Business Insider, but I found it interesting. Not for the reason of the title, Inside Microsoft's Struggle with Copilot. Yes, there are other alternatives and whatever. But I would always say, it is not that the researcher at Microsoft were not able to program an AI system that reaches up to all the expectation that users might have, but maybe there are simple inherent system limitation by our AI systems as those that I've shown you here in this video. I mean, look at this. From this publication here, how IT leaders view here this AI implementation. Never mind the name or the specifics. It is a general statement. No? And these are the results of an October 2024 survey of 132 IT leaders. Thank you, Business Insider. So go read it for more information. Just give you here very short information. And you have here this, what do they think? No? Employees struggle to integrate it into their daily routine, 72%. Engagement declines quickly, 57%. Rollout delayed due to security concerns, 40%. Has some benefits but unlikely to meet expectations, 34%. And then provides significant value to the organization. And I think this is now something that is connected to the expectation that we have as humans, as customers. And of course, it is the marketing hype that the seller, Microsoft, generates to sell this product. But I think somehow all comes together, and the expectation that we have, given the marketing announcement, is something that is not grounded here in real research. So, if from your 132 IT leaders in the sector, they say only 3% claim that this new AI provides significant value to the company, to the organization, you see the trouble that this company, but I think it's the whole AI sector, is in. Now, I believe the market has its own dynamic, and whatever happen will happen. And yes, Microsoft really plays its card, fully focusing on AI and thinking about Facebook and Meta, about the metaverse. You might ask, hey, what we learned? Wow. But you know what? Maybe AI now, with its predefined paths from its pre-training data and its pre-trained solution that is now baked in, maybe AI, the way it is and the way we understand with this new publication by Harvard, MIT, and Cornell University, maybe AI is enough. Maybe we understand, after all, AI is a great tool for us. And AI offers new possibilities. But maybe the hype and the marketing and all the videos and all the publication now of super hyper intelligence of AI, maybe we have to refocus our expectation and also the marketing slogans maybe and come to terms what AI is. AI is a great tool, and AI is a great tool with limitations. And AI is great also in its predefined path of argumentation, of causal reasoning, of logical analysis. And if we have the right pre-training data sets that AI can learn this, those pre-trained solutions are great. If suddenly those pre-trained solutions that were best in class and maybe only available to the top 1% of companies, and now with AI, we can diffuse those best in class methodologies to the rest of the 99% of the companies on this planet. This would be an extreme successful, diffusion process, no? So, the latest AI research tells us clearly about the limitation of AI and that we should not expect here AI as this super hyper-intelligence. We should understand that AI is a fantastic tool with limitations, and if we understand the limitations, we can use this tool in great ways. I hope you enjoyed this video. I hope it was informative, maybe provided some new insight, and it would be great to see you in my next video.